Okay, thank you very much for the invitation, for the kind introduction. And yeah, I will jump into it directly. So we are talking about catalysis, but I will spend most of the time with the supports. I mean, so that's the leitmotif of the talk. Just briefly, I mean, the green cat group, so that's the small group. You will see how small at the very end of the presentation, where we work on these topics. So we focus on the catalyst, and we approach it from different angles. So we start with synthesizing our catalysts to know what we have. At least we think we know what we have. I should make the distinction. And then, of course, we try to characterize them by a range of different methods, and we test them, and the reactions were pretty much mentioned. So anything that is concerned with biomass tends to be of interest, but it's mostly some hydrogenation reactions, also some condensation reactions, and we try to understand what is going on. So I will start with a take-home message that I put here on this slide. The motivation behind is that it seems to me, and it's only my personal reflection of the things, that okay, we say we have supported nickel or whatever, and that's it. And then we talk about the nickel for hours, and we maybe mention, okay, the support is alumina. But lately, we have the feeling in our group that there is more to the support, and I will try to demonstrate this with two examples, some recent examples of work that we have done. So, as I mentioned already at the beginning, so I'm trying to let's say, turn the tables, and the support now will be in the lead role. So first, however, I will touch upon some introduction. Of course, I mean, what I have here, this is basically, as we say, this is just translation from the Czech, bringing the wood into the forest, right? So I mean, you all know all about this. So of course, we need the support to have dispersion of these metals, and this would be a schematic representation. So we disperse the active phase better, and as we do that, so we have more chances for the reaction to take place. Of course, there is interaction, so we modulate somehow the active phase, so there is some charge transfer between the support and the particles, and that is also then affecting the reaction. And the last but not least, the case of the catalytic function that is really discussed. I mean, so there are such cases, and that goes typically with zeolites with pronounced acidity, and the so-called bifunctional catalysis. So we have something that, let's say, dehydrogenation that is happening here. Then we adsorb these olefinic species on the acid side because they are much easier absorbed. They can react there, isomerize, for example. The olefin moves again to the metallic side, and then it's this hydrogenated, and the final saturated isomerized product is dissolved. Well, to go with this, I mean, the support has many different characteristics that we are using to describe. I mean, and in this case, I mean, that's why we say heterogeneous catalysis, because I mean, everything is heterogeneous there. So it's not that simple, even with the specific surface area. So it's quite clear, the larger the surface, the better dispersion in theory we can have. Of course, it has its limitations. With specific supports that have organized pore structure like zeolites, we care about the size of the pores. I mean, they can be then, let's say, even detrimental to the diffusion, for example. Also, their connectivity, so the architecture is typically important in zeolites or mesoporous materials for that matter. But when we talk about the oxide supports, I mean, like alumina or titania, so this is not something that we tend to consider. Then, of course, the support has some sides, could be acid side, basic sides on the surface, and they can take part in the reaction or at least in the absorption, and so on. So that's one part. Of course, none of these are perfect, so we have defects, vacancies, and so on. So they again help us either with absorption. They also help us with anchoring our active species, let's say if it's a metal, so they can play a role in that, in the stability of those species, and let's say preventing also their sintering and so on. Then most of the oxides, so they are the endings then are OH groups, and we can have different density of those groups on the surface. And again, this has its effect on the behavior of the material. And as a specific case, some of the supports, they can be reducible or partially reducible, and that's also then changing the game as the reaction proceeds, especially when we talk about hydrogenation reactions. So we can change the support depending on the reaction conditions that we apply because of the reaction. And finally, I mentioned here impurities, and that's a general term. So that on one hand, this could be some minor components we are adding to modify the properties, but it is also things that are already from the production side in the material. So if we acquire, say, a support from a commercial company, so it can be a surprise. I mean, what we find there, and I will mention on that a little bit when talking about the titania story. That will be one of the two. Okay, so for the catalytic role, I already mentioned isomerization. So that is quite clear that we have this type of bifunctional catalyst. But this is zeolite, so it's very specific, almost silicates. But when we talk about conventional oxide supports, you don't see that very much being discussed. Might be because of the properties of the support. The acidity, for example, is not as pronounced, so maybe not taken into account that it has any significant role to, let's say, contribute to this bifunctional type of catalysis. And I think there is also another, let's say, angle to look at that for several decades we have been looking mainly on processing of petroleum, and with petroleum basically processing hydrocarbons. And in the case of hydrocarbons, alkanes, aromatics, they are typically more stable than the oxygenated compounds. And as a result, I mean, the role of alumina might be, as an example, let's say, negligible in those transformations, but this is certainly not true anymore when we talk about organic compounds having heteroatoms like oxygen. And this is something that we are looking more and more into because we try to valorize our biomass. But we have to keep in mind here that we can have modification of the metal phase properties due to the properties of the support. So that is one, but it goes also vice versa. So it's basically this interaction is mutual. So there is reaction to that. So to the primary, let's say, action. So the active phase is also affecting then what is happening to the support. And one can see that when people discuss, for example, the stability of metals supported on alumina, where adding the metals, it helps to stabilize alumina for the action of water, because alumina as such is quite, let's say, susceptible to the effect of water in the reaction mixture. And again, this is something that is, let's say, going to happen to us when we work with biomass-derived feedstock. So then they can even improve, let's say, the stability of the support. Okay, and to, let's say, wrap up the introductory part, I will just briefly look on the lignocellulose, what we have there as biomass. So we realize we have cellulose, so consisting of glucose units. We have hemicellulose, so those are the, let's say, carbohydrate parts, and then we have also lignin. That's a little bit of more enigma with very complex composition, very much dependent on the type of wood, etc. But basically, we can say there are phenolic units as the starting ones. What we will also realize from that figure that the biggest unit that has carbon bonding is 9. That would be in the lignin part. So it would be like here. There is this propyl part here, and C5, C6 in the sugars. So glucose 6 if you have xylose 5. So this is kind of where we are where we are kept, and then we can have some other molecules like extractives, abiotic acid. We can have triglycerides that are fairly popular. They have the least oxygen and are, let's say, quite easily handled in terms of conversions. But overall, we have really significant amounts of oxygen that typically we are trying to reduce. So it's quite the opposite, because when working with the petroleum feedstocks, sometimes we needed to introduce oxygen by selective oxidations, and it was quite tricky. Now we go the other way around. We try to reduce the oxygen that we arrive at materials that we need for our, let's say, daily lives. Okay, and I promised to look on the supports, and I will discuss two, let's say, case studies. First, I will look on titanium, specifically on anatase, and how this is how it, let's say, influences the reactions. I will admit, I mean, we didn't start, I mean, with looking on titanium like that. So we started the story with our catalyst, ruthenium on titanium, trying to hydrogenate hydroxymethyl furfural here, that we would get by dehydrating cellulose or glucose coming from cellulose to this type of product. So this hydroxymethylfurane and this hydroxytetrahydromethylfurane. So molecules that we can imagine would be useful as diols for synthesis of polyesters. So that is the idea behind. And typically, I mean, in the literature, this type of catalysts are reported with platinum, gold, and different types of products like this 5-MF reported as well, suggesting, okay, there is hydrogenolysis happening here of this OH bond, and we get this type of product. So we started looking in our system with ruthenium, but when checking the titanium alone first with rutile, nothing was happening. So we slept for a while. I mean, not literally, but just thinking that everything is fine. But then we realized that not all is fine with the case of some of the anatase materials, and that brought us basically to this, let's say, discussion on the intrinsic activity of the titanium in the system. And yeah, there is just a different type of applications that we could see for these materials derived from HMF. So here, I mean, yeah, the pictures are identical in this case, but I mean, that's what you would say. Okay, I have the white powder, right? I mean, whatever that is. So, but then looking at the conversion, it's quite substantial, over 3 hours, nearly 50%. So this is not something you expect from a, let's say, inert support. And we could see then, okay, we have mainly these two products. So we were wondering how these are formed. So we did several, let's say, investigations, and we looked specifically into the properties of these supports of different titania, and then also into their activity. So first, what we started with, because we had two samples of anatase. One is marked with S, because I think it came from sample A, so that's, I mean, the name. The other one is starting with A, just I guess for anatase. And the B type here, that was a material that we prepared ourselves in the lab, starting from titanium butoxide. The reason for that was that one of those titania contained, let's say, a measurable content of sulfur. So we didn't know if that could affect the activity of the material. There was also niobium I think in the other one. So I mean, yeah, we didn't know how these materials were produced. So that's why it's always good to have the chance to prepare the material on our own. So we have that. Then we treated the materials at different temperatures, just to see how they change, and we characterized the properties. So here are then the summary of the names. The number is basically the temperature used for calcination, and this A, B, and S are just the number of the supports. This is a too big table to be studied now, and it's just summarizing the properties of these materials, and you can see already here that they vary in a range for the crystallite side from XRD. In an order of magnitude, you can see also here the change in the phase composition, especially with the B type that then is turned into rutile. It is high temperature. It's something that you would expect, but it was not, let's say, happening for the A type, so already treated in the production in some way that basically it's stable another space. And then it's reflected also in the other properties, and I will discuss those in more detail as we go. So here, first looking at the XRDs, so confirming that we have anatase with the exception here of this curve that you can see. And here also other properties determined, so BET surfaces, and then in the opposite direction is the change in the size that we are determining just from the XRD for the crystallite sizes. Okay, this is corroborated also with these DEM pictures that we can see that in the A type the particles are significantly larger than in the other two materials. So that was, let's say, the basis. We then looked into the surface, into the acidity of those materials, and these are spectra of adsorbed pyridine. So before treatment, I mean, that's the D line here, and this is adsorbed pyridine, this is evacuated, and this is evacuated at higher temperature. What we can draw as a conclusion from here is that we don't have Bronsted acidity in the material, that they appear to be simply Lewis acids. And also we can see there that when we now plot this measured data versus the BET, that there is some sort of, let's say, dependence between those. So the larger surface, the more surface groups on the surface that are able to absorb pyridine and behave as Lewis acids. As a second method that we have used for probing the surface was the adsorption of isopropanol in this case. And the motivation was also a little bit different, that we were preparing at the same time materials combining silica and titania, and we were after distinguishing those two, and the OH groups in silica and titania should be distinguishable because of the different desorption maxima with the temperature of the maxima here. So, but we measured it for the series of the titanium materials, and the data are presented here. And mainly, we could observe that we have propene here as a desorbed product, let's say. And here, then plotting this signal versus PET, and you see a very similar dependence what we have seen already for the acidity. Here, on top of having only the calcined samples, we have the reduced samples. I mean, this is, to be correctly probably said that it's samples treated in hydrogen, because in this case we didn't have fluorine there. But the idea was to treat it in the same way that we, let's say, minimize this effect of different treatments. But I have to admit here that this is, I mean, doing it in the same way, but I don't fully believe it's the same way, because the ruthenia will play a role on the titania in terms of activating the hydrogen, which is something that the titania alone can't do. And since there will be activated hydrogen, it might still be affected in a different way. And that's a part, let's say, of the continuation story. So it's we are not there yet. And here also then plotting the dependence versus pyridine. So again, there is some sort of trend that we can observe. So with this characterization data, we then looked into the catalysis, although we go sequence by sequence, so we did the catalysis quite at the very beginning. And here you see then 0.5 gram of catalyst, standard par autoclave, HMF in solvent with an internal standard, so we could follow what we have there, because with these oxygenates is always to know what are the products. So, and we looked at a couple of different things. So here it's demonstrated on this S support calcine at 400 degrees C. And what you see here, when we compare the reaction in hydrogen and nitrogen, we would say they are identical or close to identical. So that basically confirms that we don't need hydrogen to obtain the products that I have shown, meaning that most likely the hydrogenolysis pathway is not the real one that is happening there, because if there is no hydrogen, difficult to hydrogenolyze, right? Yeah. So then also looking at the effect of the mass of the catalyst, that's something that you would expect, so that's not surprising at all. The effect of pressure was basically negligible in this case, so showing that okay, the reaction is happening on the surface without involvement of whatever we have in the gas phase, and then increase with the reaction temperature, again something that you would have expected. The reaction rate is going to increase, and you will have higher conversion of HMF. So that was just shown for one of the catalysts, comparison of the parameters. And then we plotted this for all the catalysts, the conversion here under the same conditions. And you can see that there is quite some differences. And the highest activity I will then show on the next slide, but that comes with the materials with the largest surface, largest concentration of the surface size. And I already showed that we have these two products. What we can see on top of that they are formed in equimolar amounts. So this is somehow connected. And then it paid off, I mean, to look into the literature also. I mean, not the literature after 2000, but literature before, between the wars, actually, so 1930 something. And there's a very nice paper by Atkins, who you might know as because of the Atkins catalyst. So, and they did some interesting work with benzyl alcohol at that time, forming then benzaldehyde and toluene. So again, similar type of reaction, because we have an aromatic compound here as well. So we believe that the reaction happens here as sometimes point in the literature as disproportionation. Personally, I don't like the name because I don't think it's disproportionation, but I wasn't able to come up with a better name yet. So if you have some ideas, I'm definitely open to them. So that's this is the products we have, and well, if we extrapolate this, so this is going to be quite reactive molecule that we can see having a ruthenium in the system or any other metal. This could be easily hydrogenated back basically to HMF. We could see this production of this product in significant amounts rather selectively. And we also see that with the ruthenium system. So this is something that basically shows that okay, we don't have to hydrogenize the bond here in order to form this the bond here in order to form this product. It's only that the lifetime of this intermediate will be very short. Here showing them how this conversion depends on the parameters that I have shown before. So on the pyridine concentration, on the adsorbed on the material, on the propene desorbed, and on the surface area. So again, this is somehow nicely correlating together. So here, just trying to show the scheme how it would look like to get into these products on the surface of titanium. So with an intermolecular hydride transfer would be our conclusion. So to wrap up this part, you could see that the titanium, even though it's the anatase, can differ greatly in the properties, and this then has a profound effect, these variations, also on its intrinsic activity in the reaction. And I didn't show that, but we were able to exclude this contribution of the impurities. So we tried to introduce sulfur in the material, didn't play a role, and also this B-type material that doesn't have any impurities is behaving nearly the same as the A-type. It has had, sorry, S-type that had the impurities, and they were quite similar, let's say, in terms of the surface area. We were not able to get as high surface area and hence concentration of the surface sites as in the S-type, but it was close to that. So we believe that the whole reaction happens through this hydride transfer, and we can obtain this product even without hydrogen, even without metal, with significant yields. And with a little bit of metal, basically we could have a selective production of this 5-methyl phosphorate. Okay, so this is for the first part, so that covering titania. And now I will shift to completely different topic, and will look on alumina. Now I will not be exploring, many types of different alumina, so it will be just one, but we will be looking specifically actually at anisole and its conversion over nickel and copper modified alumina, to show that also there are sites in alumina that are intrinsically active in the reaction, and that copper in this case especially helps to improve the stability of alumina alone that is otherwise deactivating when being reacted with anisole quite quickly. Okay, here is a little bit about the motivation, and it happens to me, I would say, always that we have some intention that is described here, but then when we start working on that, we find these small things that we try and need to clarify, and then the focus is somehow shifted a little bit. So when we started, it was quite clear, okay, anisole, it's a simple molecule, nothing can go wrong with that system. Everything is described, there is many papers, and our main motivation for this project was to look at how phenolics would behave in presence of furanics. And the motivation comes from the fact that we are generally dealing with bio-oils as a one way of processing biomass into chemicals and fuels. And in that system, of course, you have hundreds of molecules. So to really understand what is happening is really difficult. That's one extreme. The other extreme, on the other hand, is that you take a single molecule, as we did here, guaiacol or anisole, and you work with that and make conclusions. The conclusions in that case are, I would say, perfectly fine until the moment that another molecule to the system, a different type of molecule. So you add, for example, guaiacol to anisole, and the game is changing on the surface. So there is competitive effects, and so we wanted to check how this would be for the furanics, and we are still working on that topic, because we got stuck a little bit with this anisole. So we prepared catalysts by simple impregnation, and here we then had nickel and copper 10%, either this or that, on alumina. We also prepared mixed samples, and again that goes outside of this because not understanding everything yet properly. And so here, just to show, okay, we have the copper there, we have the nickel in the system, and okay, we have some drop here in the surface area, but nothing that should worry us. In this case, we were performing the tests in a small tubular flow reactor, so that's highlighted here, and you can also see the conditions there. We tried to work in quite a wide range of temperatures, so really to cover the area, and also quite a significant range of contact times or space velocities as shown here. So to really vary the conversion significantly over in the reaction system. And I will be focusing here primarily on anisole because it's a simple molecule. The conclusions for guaiacol are very similar, but there is one specific fact that I will mention when I do that. Okay, then we looked at the acid sites because that's always with these materials that you need to absorb your reactants. So we were looking first on the acidity. Here it's ammonia, TPD. And here we have, okay, desorption of ammonia. Then we have the catalyst as prepared, so after calcination. So it's nickel oxide, will be probably correctly here. Also desorbing ammonia, but then we have reduced nickel on alumina, and the situation is changing a bit. The reason for that is that ammonia obviously can absorb also on the nickel sides that might have, let's say, certain acidic, fluid acidic character, but it is not desorbing. Rather, at these conditions, it is decomposed into nitrogen and hydrogen. So that is a little bit changing. So when evaluating this, let's say, semi-quantitatively at least, so we have the alumina case here, so total, and the sites A that are those that are absorbing and desorbing ammonia, and this we reserve then for the sites that could absorb ammonia, but it's not dissolved from there. What you will notice that here the number is, I don't know if by accident, the same, but on the acid sites it's decreased because we have this, let's say, 20-25% of sites that are other sites, but in the non-reduced case, this coincides the number here. So we reduce these sites and these are not existing. So from that, the conclusion is that there are some sites in alumina that are occupied or blocked by the nickel oxide form, but then when reduced, I mean, either they reappear or rather the nickel itself takes the role of these sites. So this is one thing, and what comes in some kind of correlation with that is the study of absorption and desorption of anisole done in a TPD instrument. So we see here that we are absorbing anisole on alumina. Then we have nickel on alumina. This is less, again, close to 20%. So from here, we would conclude that the anisole is really primarily absorbing on the alumina surface, or not on the nickel. So, and that these fluid sites that I was showing before by ammonia TPD are the sites that are responsible for absorbing anisole there and activating. That's what we have then seen when I say activating, that when we did this at higher temperatures, so we not only had absorption, but the system started already reacting. And what is more curious is the, let's say, type of product. So here's the anisole, kind of, let's say, breakthrough curve there, but you see here forming phenol, that you would say, okay, phenol that I would expect, I cleave off the methyl from there, but then we have this type of methylated products. And that caught our attention, I would say, because suddenly we could see, okay, the methyl is not lost, not going to form methane as a not so valuable byproduct, but we can keep it on the aromatic ring in this case, because we have methyl phenol, methyl anisole, dimethyl phenol here as products in different quantities. And the distribution looks fairly similar when we have nickel on alumina. So yeah, seemingly we have really the role of alumina in this case that is quite significant. And we treated also the material after this with hydrogen, and we could see that we are desorbing methane from the surface. So that is up here. And together with that, we also saw toluene, benzene, and also a bit of phenol. So this is kind of suggesting that the methyl that is transferred to the aromatic ring is in between. It's, let's say, stored on the surface of alumina. So that is basically kind of transfer through that. But this is something that we still need to work on and prove if it's really like that or if it's a bimolecular reaction between the two anisoles. So this is still work in progress. But I mean, for us, the main conclusion was that alumina is responsible for absorption of anisole and also for this demethylation and methylation reactions that are, let's say, represented by the reactions that you see there. Here, that's how it, what could be the possible reactions. And as I mentioned, we still wonder that, okay, is it a bimolecular reaction? And do we have demethoxylation there? And then only to the alumina, and then only the methyl being transferred, or is it demethylation? So this is still things that are not clear, not only to us, but I haven't seen this in the literature that, I mean, that would have been, let's say, described and explained to the full extent. Then also, I mean, running the reaction over, let's say, different temperatures. So we see here increase in anisole conversion. Here, this is nickel on alumina, and then the situation is changing because we have nickel there. Of course, that's a good hydrogenation catalyst, and then the reaction pathway takes a different turn because we saturate the ring. We form methoxycyclohexane as the primary product. That is then demethoxylated, most likely to form cyclohexene. I would say that is converted then to cyclohexane, and we see also benzene. One could speculate that the benzene could be formed by direct demethoxylation of anisole, but we believe it's not the case, at least not in these catalysts, that in reality it is formed from cyclohexane, or from cyclohexene actually. It will be the primary product of demethoxylation of this methoxycyclohexane. And I mean, to support this, we have done experiments with this methoxycyclohexane. So we took one of the experiments where we were yielding even more of methoxycyclohexane and started the reaction with methoxycyclohexane. And surprisingly, or maybe not, the distribution between benzene and cyclohexane as the ultimate product was exactly the same. And we could also then see that when calculating the thermodynamic limitations at these low pressures, so already it gives a chance, especially at the higher temperatures, for the hydrogenation reactions to be, let's say, preferred, or not to be, to be preferred, like that. So this is basically then suggested down here in this scheme. And we also then see the formation of these other products of the methylated benzene and cyclohexanes, because we are able to saturate the aromatic ring. And then, of course, the distribution is highly dependent on the balance between the activity of the nickel sites and of the alumina support alone. Well, when adding copper to the system instead of nickel, so we don't see any hydrogenation reaction. So the copper, even reduced, is not able to activate the hydrogen in the way that we would be hydrogenating the aromatic ring. This is not happening. But we see again these methylated species, and we see higher conversion. And this we attribute to the improving the stability of the material. So we have run the test that we kept in the flow reactor at constant conditions, and while we see a rather fast decline in the conversion when operating this reaction only with alumina as a catalyst, in case we have copper or alumina, the decline is much slower. And what is quite nice here is that when you look at the points obtained with copper that's the circles, and with alumina, so that's this asterisk here, so they follow the same trend when plotted versus the conversion. So this is a way that how we could improve the performance of alumina alone to yield these type of products. And of course, since we don't have the aromatic ring hydrogenation, so we have much lower or much less products. Well, this is then how we can make the things complicated with this simple molecule of anisole. So looking at this, you can see the different ranges by color coding. So at the lowest temperatures, we have favored the hydrogenation step that you can see here, only the ring hydrogenation, and then we can have the demethoxylation here and forming cyclohexene that has two possibilities, and depending on the conditions, it's gonna go to cyclohexane, dehydrogenated, or at higher temperatures, it will be dehydrogenated in this direction. And then we also have this, what I was discussing for the most of the talk, different methylation reactions occurring there. And apart from that, we still see also some condensation reactions on top of it. So the system becomes fairly complex. And yeah, that brings me to conclusions on this part. So the alumina has multiple roles in the catalyst. Most importantly, in this case, it provides a site where anisole is absorbing, so we need to activate, but it also initiates transformation of anisole. Could be some sort of dissociation. So we have the aromatic part and the methyl methoxy part, and they are apart, and depending on the conditions, we either attach the methyl to the aromatic ring, or it can then be in excess of hydrogen dissolved as methane from the surface. And this is still something that we need to investigate more to see how it is with these methyl methoxy groups and so on. And these active surface sites, they are definitely affected by the metals we incorporate there. So we clearly see that we modify the properties of alumina, let's say by adding copper or nickel there, and this can be helpful in fighting the deactivation of the catalyst, which is of course one of the big challenges in any biomass. Okay, and with this is just few overall statements. The oxidic supports are on its own quite complex, and let's say, or referring to your project, one could frame the complexity in many ways here, and yeah, we have already used the help of some of you in looking into these materials, modified with ruthenium, and trying to see that how we can really understand what is happening there. Okay, so I would like to thank the group with whom I am working in Prague, and also for the financial support to the Czech Science Foundation. And thank you very much for your kind attention.